All right, today we're going to plug into one of the biggest, most important rivalries in the history of science. Seriously, this was a battle of titans, a total clash of ideas that literally wired the world we live in today. This is the story of the War of the Currents.
And look, this wasn't just some friendly debate between scientists. No way! We're talking about massive fortunes, reputations, and the entire future of electricity hanging in the balance. You had Thomas Edison on one side, right? The established genius. And then on the other, you had Nikola Tesla, this brilliant, kind of outsider visionary with a totally revolutionary idea.
So, who actually won? I mean, who won the war for the outlets right there in your wall? Well, think about it. Every single time you charge your phone or just flick on a light, you are literally plugging into the outcome of this epic fight. The answer is flowing through your home as we speak, but the story of how it got there, well, it's pretty shocking.
Okay, so to really get what this war was all about, we have to understand the weapons, right? The two big contenders were direct current, or DC, and alternating current, or AC. Now, they both do the same basic job, get power from A to B, but they do it in ways that are just fundamentally different.
So the really crucial difference here is all about the flow. Edison's DC is super straightforward. The electrons just move in one direction, kind of like water flowing through a pipe. Simple. But with Tesla's AC, the electrons don't really travel anywhere. They just vibrate. They move back and forth, constantly changing direction.
Yeah, a perfect way to picture DC is like a steady, powerful river. It's predictable, it's constant, and it's always moving in one direction, downstream. And this was, the first type of electricity that was ever really harnessed and sold to people.
AC, on the other hand, is way more like a swing. The electrons aren't making some grand journey across the country. Nope. They're just moving back and forth, right in place, transferring energy as they go. I know it sounds a little less intuitive, but believe me, this back and forth motion, well, that turned out to be AC's secret weapon.
But back in the early days of electricity, Edison's DC system had this one huge, glaring problem, a problem that basically kept the lights off for most of the population. It all came down to a simple problem of distance.
And this inefficiency, it was a huge problem. See, because DC lost so much power over any kind of distance, you needed a power station on practically every single city block. Just imagine that. It made electricity a total luxury item, something only the rich could afford in big cities. It was a massive roadblock to, electrifying the entire world.
Okay, so this is where Nikola Tesla and his alternating current really enter the story. Tesla saw that the weird back-and-forth nature of AC actually held the key to solving this whole distance problem, and it all boiled down to one just incredible invention.
The absolute game changer was the transformer. You see, with AC, you could easily step up the voltage to these incredibly high levels. That meant you could send electricity hundreds of miles with barely any power loss. Then, when it got near your house, another transformer would just step it down to a safe, usable level. This one simple device made a huge, widespread power grid not just possible, but affordable for everyone.
Okay, so AC totally won the distance war, right? But it created this new kind of mind-bending puzzle. If the current is always flipping back and forth, from positive to negative, what's its actual value? How on earth do you measure something that is constantly changing?
And this is the paradox right here. For every little push forward, there's an equal pull backward. So, over one complete cycle, the electrons basically end up right back where they started. Which means, if you try to take a simple average of the current, the answer you get is zero. A big fat zero.
So, if the average is zero, how can it possibly power anything? That was the critical question. A current that averages out to nothing sounds completely useless, right? But it was obviously lighting up bulbs and running motors. So how do we measure its effective power?
The answer is a clever bit of math called root mean square, or RMS for short. It's basically a special way of finding a meaningful average for something that goes above and below zero all the time. It gives us a number that tells us the equivalent power you'd get from a DC current. It works in 3 simple steps. First, you take all the current values and you square them. Now, this is the brilliant part, because squaring a negative number makes it positive, right? So suddenly, the whole wave is positive. Next, you find the mean, the average, of this new all-positive wave. And finally, you take the square root of that average. And bam, you're left with a single, useful, positive number that tells you the effective power of that AC current. Pretty smart, huh? So when you hear that the voltage in your home is, say, 220 volts, they're not talking about the average voltage, which we know is 0, and they're not talking about the peak voltage either. They're giving you that RMS value. It's just the standard way we all talk about AC power.
Okay, so this brings us to a really important safety question. Let's say you have two wires. One has 220 volts of good old DC. The other has 220 volts RMS of AC. Which one is more dangerous? Which one would you really not want to touch? The answer might actually surprise you.
Believe it or not, the AC wire is way more dangerous. And here's why. While its effective, or RMS value, is 220 volts, the actual voltage is swinging way up and way down. And at its peak, that 220-volt AC line is actually hitting a staggering 311 volts. And it's that peak voltage that delivers the really nasty shock.
So, after all that fighting, did AC just win the war outright? Well, not exactly. That fierce rivalry between Edison and Tesla, it eventually cooled off and turned into a kind of partnership that, today, powers our entire modern world. You see, AC definitely won the battle for the grid. It is the undisputed champion of getting power from the power plant all the way to your home efficiently. But the second that power goes into your laptop or your TV or your phone, it's a DC world. All of our sensitive electronics, they need that steady, stable flow that only direct current can provide. So how do we bridge that gap? Well, we use a little device called a rectifier. You can think of it like a translator or maybe a peacekeeper. It's the thing that lives inside that little power brick on your charging cable, and its entire job is to take that wild back and forth AC from the wall and convert it into the calm, one-way DC that your devices crave. And this little journey happens every single time you plug something in. High voltage AC comes screaming out of the wall into your charger. Inside, the rectifier does its magic, transforming it into low voltage DC. And that's the clean, safe power that charges your battery. Pretty much every electronic device you own is doing this exact conversion, all the time. So in the end, the Great War of the Currents didn't really have a clear winner. It ended in this perfect partnership, a symbiosis. It was a conflict that gave us the best of both worlds. And, it kind of makes you wonder, as we look ahead to things like renewables, battery storage, and smart grids, what's going to be the next great energy battle that defines our future?